Today, we're going to set up some more integrals using solids of revolution. All of our integrals have to come from some multiplication for now. All of our integrals are going to come from some form of multiplication. In this case, we're going to multiply area by height to get volume. So the area here is the cross-sectional area, and that's how we're going to get volume. So what we're doing is we're forming a solid by rotating a region about an axis. So if let's think about a couple of simple versions of this. Let's suppose that we take a region that's a triangle, a right triangle specifically, with some base and some height. And let's suppose that we want to rotate this triangle about an axis. So the axis, let's use as an axis, just a vertical line through this vertical leg that I've labeled with the height. And so we're going to rotate it around, rotate the solid, the region around that axis. So we'll end up with a cone. And the axis that we rotated would go right down through the center of the cone, hit the center of the circle, and come out the bottom. The height of this cone will still be h, and the radius of the cone will be the base of the original triangle. It was windy yesterday when I was working on this, so that's why the cone is a little bit off to the side. But our original triangle can be seen right in here. Right there. So it's like those holiday decorations where you can fold them flat, and then to set up the decoration, you just take that the region and rotate it about. You unroll, and it's all this folded and glued paper in the middle, like a honeycomb pattern. So if we take, let's say, a rectangle, with some length and a width, and let's rotate this around an axis. This will give us a cylinder. And the axis of rotation would be going right through the center of the cylinder. A cylinder, the width of the cylinder will be the width of our original rectangle. And the length of our rectangle will form the radius of the cylinder. Our original rectangle will be in here. So here's how we're going to form a solid. Another thing that we might do in both of these cases, the axis of rotation has been attached to the region. The axis of the rotation has been a boundary of the region. So another way we might set up a solid is to imagine a region I'm going to use a triangle again with a height and a base. But instead of rotating it around a boundary of the region, we'll leave a space and we'll put an axis that's not a boundary of the region. So in the first two examples, we had an axis that is a boundary of the region. And in this case, the axis is not a boundary of the region. So that's how we're going to classify things. Any questions? Oh, I got to draw my solid. So what's going to happen is we're going to get a solid, but the solid's going to have a big hole in it. So we're going to have to define a new quantity for this region. So the base of the triangle that we're going to rotate around this axis is part of it, but the other thing that we're going to need is, say, this distance. I'm going to call it the radius because we're rotating something. We're also going to have this radius as a hole through the center of our solid. So for some reason, I'm going to still attempt to draw this, even though I have a distinct lack of drawing skill. Which should be keeping me from teaching Calc 3, but they keep giving me Calc 3 classes, so I don't know. Keep telling them to stop, but keep showing up on the schedule. So our axis of rotation is going through this big hole in the center of our solid. It's going to go back that way. That's not so bad. It's come out a lot worse in the past. Our original triangle that we rotated is going to be here. So here's our original base for the triangle. Our height is still where we left it. And this hole in the center of our solid is going to be cylindrical with a radius of r. So here's going to be another length r. And here's going to be another length b. So we want to set up definite integrals to find areas of these solids. Keep in mind, we're not doing this because in your future career as a fill in the blank, you are not going to be finding volumes of solids of revolution, because chances are there's going to be some better way to find the solution. But finding the solution is not the point. I know this is a math class and everyone's like, oh, math class is about finding the answer. It is most definitely not about finding the answer. Maybe one of the reasons that we are as a society so bad at math, as a society in the general population, not as the, math portion of society. But as a society, maybe one of the reasons that we're so bad at math is that we have such a small view of what math is about. How it's just about getting the answer. There's always just one answer. There isn't always just one answer. There isn't always just one way of doing things. The whole point of being in math class is to learn all the different ways of doing things to find out which one is right for a given situation. Context matters. Your audience matters. I know you hear me say that a lot, but that's because I think it needs to be said. So I'm gonna say it every chance I get. All right, so we need to break these down into volumes where there's a cross-sectional area multiplied by a height. We need to slice things in such a way that the area can always be found with the same shape. Since we only get one variable, we can't vary the shape of the area. We can only vary the size of the area. That's an important thing to keep in mind. So when we do cross-sectional area multiplied by height, we can't vary the shape of the area. We can only vary the size of the area. If we want to vary the shape of the area, we're going to have to involve more variables. But we're not allowed to do that because this is Calc 1. We have decided to place this big restriction on ourselves. Instead of using lots of variables to do a thing, we're just going to use one variable. So let's begin with an example. Let's take the region Let's consider the region. Let's use a region that we've used before. Consider the region bounded by y equals x squared, the y-axis, and y equals 4. I think I did 2, 4 when I did the x squared version. So let's do that. So let's consider y equals x squared. Put this line up here at y equals 4. Here's our x-axis, our y-axis. This is going to happen when x is equal to 2 in case we happen to integrate that way. Let's find the volume of this solid when it's rotated about the y-axis. Find the volume of the solid formed by rotating the region about the y-axis. So we're going to use the y-axis and rotate about that. One thing we might want to do is think about what the shape will look like So let's think about what the shape will look like. I'm going to have this parabola shape. It's going to be a parabola and then flat on top and then flat on the inside. And I'm going to rotate it around. So we're going to create this circular paraboloid, which is just kind of a bowl shape. An important thing to note is at the bottom of this bowl, since the function goes flat here, the derivative of x squared at 0 is 0, so it's going to be flat. And our axis of rotation will go right down through the center of it. So here's where we rotated. Down here at the bottom will be the x-axis, and up through the axis of rotation will be the y-axis. I don't need to put that. So we're going to get this circular paraboloid. So sometimes it helps to picture what the thing looks like. But more importantly, if we're just going to be looking at formulas, we need to know what the name of the thing is. And that will help us look up the formulas. But since we're doing calculus problems, what the thing actually looks like is not really relevant to our interests. What is relevant is that we be able to see what the shape of the slice is going to be, so that we can multiply the cross-sectional area times the height, and then add up all those volumes. So, like I said before, we need to slice this region, or sorry, this solid, so that the shape of the slice is always the same. We need to slice so that the shape of the slice is always the same. Its size can be different, that can be the variable, but the shape has to be the same. Okay, so we need to find slices where the shape is the same. The size can be variable, but the shape needs to be constant. The size can be variable, but the shape needs to be constant. So looking at this circular paraboloid, if we slice it vertically, we're going to have a bunch of we'll have a bunch of parabolas. If we slice it horizontally, we'll have a bunch of circles. Gives us a few choices. And as we've seen before, choices are trouble, because then we have to decide. I don't know if anybody remembers the game Skyrim, but one of the difficult things in Skyrim is like, oh, well, what am I going to do now? Because you could just kind of do anything that you want. There's not like a line of things that you have to do. It's like playing in certain D&D games. The DM says, like, oh, well, what are you going to do? And the players is like, oh, I don't know. What's the main quest? Who's got an exclamation point above their head? So, and then some players, you give them someone with an exclamation point above their head, and they're like, oh, hey, we're going to go do this other thing. What happens here off the edge of the map? And the DM's like, oh, stuff. He's like, oh, great, let's go find out. I'm like, oh, okay, I guess I'm drawing an entirely new map. So we have choices. We can slice this with a bunch of parabolas, or we can slice it with a bunch of circles. That's the one that we're going to pick. So let's slice this. If I slice this horizontally, we will get circles. There'll be a point down here at the bottom, and then it'll be circles all the way up. Instead of turtles the whole way down, it's circles all the way up. Then we have to think about what that's going to look like in terms of our picture. If I slice horizontally into the circles that we're going to see are going to be this part of the region. The circular slice is going to show up as a horizontal segment in the region. Now this piece is getting rotated around to the other side. So every time we make a horizontal slice, we're going to slice a circle out of our circular paraboloid. Our strategy is the same strategy that we always use in integration. I want to do multiplication. To do multiplication, everything has to be constant. Our factors need to be constant. So I'm going to use this radius for a little small change in y. That'll show up on the other side after we rotate. The other piece that we need is the radius of this slice, because it's a circle. And so here's the radius. So we're going to take the area of a circle, pi r squared, and multiply by the height, delta y. That's using, and we're going to assume that the area is constant for some small change in y, because if I make the change in y small enough, the area isn't going to change all that much. Now we need to relate this into terms that the region can understand. And since we use Cartesian coordinates, that's what we're going to use to define our radius. Pick a point where, take the point where the slice hits the boundary, x squared, and label your x and y, label your variables. Like I mentioned yesterday, the number one mistake that y'all are going to be making when you try to do these problems is that you're not going to label things on your diagram. If you're not going to draw labels on your diagram, why bother making a diagram? So we're going to take the area of the circle, pi r squared, and multiply by the height, delta y. That's us using multiplication to get the volume. Then I'm going to add up all such volumes, and then that will give us a Riemann sum. We'll make the number of slices go to infinity as they become infinitely thin, and that'll turn into a definite integral. Any questions? The last thing that we're going to want to notice is that we are integrating a dy. So we need to integrate where there are the y values where there's a slice. So this is going to start off at y equals 0 and stop at y equals 4. Part of setting up the integral is getting your interval correct. The other common mistake that we're going to make when we're setting up definite integrals is to set up an integral dy, but then integrate from 0 to 2, because that's where the x's are. I'm not saying that this is because calculus books lack imagination, but I think it might have something to do with the fact that calculus books kind of lack imagination, and they look at all these problems as separate rather than trying to factor out what the overall method is. And when you read a calculus book from a teacher's standpoint, it's very clear that they're explaining a method that you can apply to all these problems. But that's because the book is, we're not really consulting students that don't know what we're talking about when we're reading the book, when we're writing a textbook. Like I've written a textbook. We just kind of like do things that make sense to us as instructors. No, I got your gator. My dog brought me his gator. Gator has made an appearance in class. Hey. My dog thinks this particular topic is boring. Don't you, buddy? You know what I'm going to do? I'm going to put you on camera. You don't like having your picture taken. Should I put you on camera? There he is. Got your gator. Got your girder. Got your girder. Look, Colson, you're on camera. Say hello. Oh my God, that's embarrassing, Dad. So, no, there's nothing that will make my views skyrocket. Unless I call this dog interrupts. So that's one of the things I'm not worried about. I am absolutely not worried about going viral. He is a big boy. He is 123 pounds. He's a little fat at 123. I would rather have him at 120 pounds. But he is a big boy. Aren't you a big boy? Gonna give us a growl? Okay. Okay, I gotta finish this class, buddy. All right, so let's turn the page and set up our integral. Hashtag branding. So our volume is cross-sectional area multiplied by height. The cross-section is a circle. So for the area, we're going to use pi r squared. And the height is a delta y. This means that we're going to have to write r in terms of y. What we notice on our diagram is that r is equal to x. So we notice on our diagram that r is equal to x, but that ain't no good. We need it in terms of y. But thankfully, x and y are related since y equals x squared. So since y equals x squared, that means x equals the square root of y. And so now I can write the radius in terms of y. So if x is y squared, sorry, if y is x squared, then x is the square root of y. So r is equal to x, and x is equal to the square root of y. Oops, here's what I'm writing. So for the volume, I have pi times the radius squared times the delta y. And for the radius, I need to write it in terms of y, which was the light blue, and y, r is the square root of y. Now we need to add up all such areas and turn this into a definite integral. So there's a Riemann sum. And then this is going to give us a definite integral. I'm going to factor out the pi. I'm going to simplify the square root of y squared to be just y. The delta y in the sum becomes a dy when it's continuous. And now we just need to integrate over all values of y, which we had a slice. And that was from 0 to 4. We usually don't write y equals when we're writing the interval of our definite integral. We usually don't write y equals because we're saying y equals when we write dy at the end. But we all are new at this writing integrals business, so I'm gonna keep doing it. It's like saying 5x minus 4x equals 1x. In practice, we don't write the 1x because it's understood to be 1x when we just write x. But in the beginning, we probably should write that 1x to emphasize what that means. This is a very simple integral to evaluate. This is just going to give us a 4 pi. But if we're just dead set against using that, we can just jump to the 90s and use our calculator to find the value. Any questions? Great. Even in a problem like this where it would be no big deal to evaluate the definite integral by writing stuff down, it's still easier just to math 9 the whole thing, even though it's just y with respect to y from 0 to 4. Oops. So 25.13. So 8 pi. Did I say 4 earlier? I pretty much do this problem every year. So I don't even know what I just said. So 25.133. Let's just leave it at that. All the engineers are just like, oh, what are the units? Well, it's volume, so it's cubic units of whatever the unit of length is that we were using. And then all the engineers are going, oh, damn mathematicians. All right. Now that we're at the end of class, of course, is when Colson starts to settle down. It's like, oh, I'm just going to go lay down here. It's like, oh, dude, I'm about to get up. And now he's going to be all quiet, which is super on brand for pets at Zoom meetings. All right, this is our new thing. The principles are all still the same. We're going to calculate a volume by doing cross-sectional area multiplied by height. The cross-sectional area has to be the same shape all the way up the height because we only get one variable, and we're going to use that variable to vary the size of the area. We're always going to have to look for that multiplication where one of the factors is variable to set up our integration. Remember, the goal is not finding volumes of these things. The goal is to learn the process of integration and to practice our analytic geometry skills. Kind of reminds me of being in a trig class when you start doing all those trig identities where you have to prove these trig identities. It's not because those are important trig identities. It's because we use trig identities to reinforce your algebra skills. Because when you walk into a trig class, I don't care what grade you got in your algebra class, your algebra skills are probably pretty weak. I'm just guessing that based on the fact that when you walk into a calculus class, your algebra skills usually are pretty weak. I'm not saying you personally. I'm just saying a lot of you are missing a lot of algebra skills because we kind of get you enough to get by and move you along because that's all we really need. We don't want to build an algebra class where to successfully pass the algebra class, you have to have awesome algebra skills. You need enough to get by. You need enough to get by and you need to avoid the bad habits. Just like learning anything else. When you're learning baseball, you don't have to learn a ton of theory about baseball. You need to know which direction to go. You need to know how to catch, how to throw, how to swing a bat. And then you just start playing baseball. And you find out the individual things that you need to work on. Same thing happens in calculus. You've done your algebra classes. you're kind of weak at algebra, even though you got an A. But it's kind of an indication that you're going to be okay moving forward. And that's really the question that teachers need to ask. Not, are you good at algebra? Because there's no way we could know that at the end of an algebra class. I have no idea if you're even good at math yet. But did they build a skill set? Did the student build a skill set that will lead to progress later on? That's the thing that we need to care about. Same thing with calculus. I don't care in 5 years if you can actually integrate things anymore. Unless, of course, you're working as a math teacher, then you need to. But that's not the point. The point is not that you're going to be integrating later. The point is that you have integrated in the past and you use that to build a skill set and strengthen your understanding of how math works and how we use math to view the world. That's the important thing. And I know I say this a lot because it needs to be said a lot, because a lot of people will say, look at a math thing and say, well, why didn't we learn X, Y, and Z in school? Why did we have to learn the stupid quadratic formula? And I always respond, well, I don't know why you learn the quadratic formula, because the quadratic formula is trash, but that wasn't the point in the first place. It wasn't about solving quadratic equations that you're never going to solve again after you get out of algebra class. And when you're making that argument, you're still arguing in favor of not knowing things. And if you're interested in not knowing things, school might not be the place for you. I don't know. You know what I mean? Don't be like, oh, I want to go to school, but I don't want to know things. At least we get at the truth of what we want. At least when someone says that, we're dealing on even footing. And they're clearly stating their thesis. I want a degree. I don't want to have to learn. I want to learn as little as possible. Just give me the degree. And then we start to understand how society really works. Oh, he's climbing on me again. And that if you have enough money, you could just go and buy the degree without learning anything. So if y'all wanted your degrees because you want to get a job, because you want to be wealthy, you've already made a mistake. You should have had rich parents. Then you would have been all right. Anyway, enough of this silliness. Go check out section 8.2, applications to geometry. I'm going to get chewed on by my Rottweiler. Come on up here, buddy. Come on up here. There you are. Say goodbye to your class. Look, you're on camera. You're on camera. Okay. All right, everybody. That's it for today. That's it for this week. Everybody have a good weekend, and thanks for playing. Home butter.